All right, so first of all, I'd like to thank the organizers for the chance to speak today. My name is Vincent Su, and I'll be telling you about a Renyi quantum null energy condition. And this is based on joint work with Mudasir Musa, who's a postdoc at Cornell, and our very own Pratik Roth, who just graduated and will be starting at UCSB. Okay. So to give a roadmap of where we'll be going, I'll start off by reviewing the QNEC, which in recent years has really shown us the intimate connection between energy and information. Okay, then I'll introduce a Renyi generalization of this statement. I'll then talk about some of the techniques that were special to free field theories that allowed us to make progress in proving this. And then finally, I'll present some numerical evidence for theories outside the range of validity of our proof. Okay, so to start, let's review the QNEC. So the quantum null energy condition is the statement that the stress energy tensor at a point is lower bounded by a certain second derivative of the von Neumann entropy of some state. So that's a lot, but the picture to have in mind here is on the right. So take some Cauchy slice. You can split it into two regions by what we call an entangling surface that has coordinates v of y, where y is kind of the transverse direction. So that's this shape here, and it has to contain the point P where we're evaluating the stress tensor. When you have this surface, you split your Cauchy slice into two regions. We call them R and R bar. And the derivatives that appear here are functional derivatives of this profile in the null direction. So here I've kind of drawn what happens if we deform this profile in the null direction in some kind of neighborhood of P that has width A. Eventually we'll take A going to 0. And notice that this null direction also makes the region R smaller. We'll come back to this later. And for the purposes of this talk, we're going to focus on what we call the diagonal part of the second derivative, meaning that we're going to take two derivatives of this profile at the same point. So more generally, you can think about taking derivatives of the entropy at different points. But here we're going to focus on taking the two derivatives at the same point. Okay, and historically, this statement was really discovered by, as a consequence of the quantum focusing conjecture. And for those of you who aren't familiar, the basic idea is that, in trying to think about how to merge general relativity and quantum field theory together, the line of reasoning that led to this was essentially to take a theorem in general relativity, elevate it to some quantum statement, conjecture that it holds in a full theory of quantum gravity, and then take a limit, a non-gravitational limit. Okay, so if you assume this quantum focusing conjecture, then the QNEC basically falls out as a corollary. Okay, and it's not really obvious how one would even think of this as the statement that's true in quantum field theory. But in recent years, indeed, this statement has been proven for all quantum field theories within the framework of QFT. So it kind of took baby steps, starting with free theories, upgraded to holographic theories, and then finally for more general interacting theories. The work I'm going to talk about today will most closely follow this original work of free field theory, QNEC, by Busso et al. In 2015. And it's worth pointing out that the general proof for interacting QFTs is like 100 pages of dense mathematics, whereas if you kind of assume this quantum focusing conjecture, it takes like about 2 lines. Okay, so the reason that I'm here presenting on this today is that really, this statement about an energy bound can really be reframed purely in terms of quantum information, and that is through the relative entropy. Okay. So as a refresher, let's talk about the relative entropy. So if you're interested in the relative entropy between two quantum states, rho and sigma, it's defined as the trace of rho log rho minus rho log sigma. One way to think about this is it's the expectation of log rho minus log sigma evaluated in the state rho. And operationally, this is a measure of distinguishability. How hard is it to kind of distinguish rho from the state sigma? And one of the basic properties of this is that it is monotonic under partial trace. So if you throw out part of your quantum system, it should only get more difficult to distinguish them. And in terms of these null derivatives that we're talking about, you can think about this as the statement that the first derivative of the relative entropy is positive. Okay, and this is true for all quantum systems. Now we're going to massage the relative entropy so that it's a little bit nicer to think about in quantum field theory. Okay, and the basic starting point here is basically by adding and subtracting this factor of the vacuum entropy. Okay, and you know, there's basically one more line or two in here, but what you can show is that the relative entropy of rho with respect to sigma is the difference of minus log sigma, or the modular energy, minus the entropy. And here these deltas refer to vacuum subtraction, or well, the delta refers to evaluating this quantity in the state rho versus in the state sigma. Okay, so you know, it might seem a little bit funny, but the reason that this is nice is because if you take sigma to be the vacuum, then minus log sigma, also known as the modular Hamiltonian, or it also goes by the entanglement Hamiltonian. This has a nice form when you restrict it to a null plane, and in particular, it becomes an integral of the stress tensor. Okay, so the reason that this is nice is if you then take two derivatives of the relative entropy, you get out the appropriate the appropriate terms out of T minus S double prime. Okay, and the fact that this derivative of the relative entropy is positive is something that's very special to QFT. It's pretty easy to write down quantum mechanical systems that violate this. Okay, and so, you know, framed this way, we can actually recast the QNEC as the statement that the second derivative of the relative entropy evaluated for any state with respect to the vacuum should be positive. Okay, so just to signpost where we are, the QNEC is really an important result that has deep implications for the structure of QFT. It's a non-trivial bound that holds in all quantum field theories. And you can think about it as being derived from constraining the relative entropy. Oh, sorry. So a very natural question is, you know, can we similarly bound other quantum information quantities? Okay. I guess I'll take a second to pause for questions. I can't really see the chat, so feel free to unmute yourself. Okay. All right, so moving on. Okay, so the new conjecture that we're working off of here is basically a Renyi generalization of the QNEC. So here, the statement we're considering is whether the second derivative of a Renyi generalization of the Renyi entropy is positive for any state with respect to the vacuum. The particular quantity we're going to be examining here is what's called the sandwiched Renyi divergence. Okay, so this is a one parameter family generalization of the relative entropy. It's valid for n between 1/2 and infinity. In terms of density matrices, it's defined as the log trace of this kind of combination of the states. You might also think about it as, you might think about it as the Renyi entropy of a so-called sandwich state that is obtained by sandwiching your state rho by sigma. Okay, so our goal is going to be to basically prove that the second derivative of this is positive. This was originally conjectured in 2018 by Nima Lashkari. In that work, he was using the monotonicity of relative entropy to constrain the structure of correlation functions. And he couldn't find any counterexamples to the statement, which he thought should be wrong. So that kind of led him to actually conjecture that it's true, hoping for some falsifications. But our goal in this talk is to show that indeed this Renyi QNEC is satisfied for arbitrary states rho in free theories.
Vincent?
Yeah.
Is the statement that the argument of the trace is a good density operator precisely for n being between 1/2 and infinity?
Oh, good. So the statement of this n range is basically so that it satisfies nice properties of divergences. So for example, one thing you want to demand is this data processing inequality or the monotonicity under partial trace. If you go outside of this range, then it doesn't hold.
Maybe I misunderstood, but you seem to be suggesting that one way to think about this is to think of the argument as a whole, as a state.
Yeah, you can do that. It is not normalized. That's the only downside.
It's positive and everything, but it's just not normalized.
Yeah.
And it's finite. Mm-hmm.
Yeah. Okay. Cool. So, so in order to make progress on this, let me first review basically something that's very special to free field theories in dimensions greater than 2. And the intuition behind this technique is that if you look at the state on some region, so the reduced density matrix on some region, it's unitarily equivalent to the state on a null plane to the future plus some relevant data at null infinity. Okay, so it's basically, you know, anywhere in the causal domain of dependence, like any slice within the causal diamond should be equivalent. And we're going to kind of push that to its null limits. And this might seem like overkill, but the thing that is very nice for free field theories is that in fact, the state on this null plane has a nice property called ultralocality. And what you can do is you can actually break up the null plane into a tensor product of what are called pencils. So this picture down here, this plane is a null plane where we've discretized into transverse directions, where these lines are the pencils. Okay, and the intuition here is that in a free theory, light-like particles won't talk to each other on different null generators. So you can really think of them as being independent. Okay, so ultimately, this A is actually the same A that showed up in our first diagram where we're deforming the surface in some region of width A. And for the QNEC, we're eventually going to take A to 0. And a couple of nice things happen. Okay, the first thing is that the state on any individual pencil will look more and more like the vacuum as A goes to 0. And the second is that our null derivatives in the original QNEC statement can basically be swapped with lambda derivatives on the pencil of interest, where lambda is like the affine parameter on that pencil. Okay, and what's particularly nice about the Renyi QNEC for free field theories is that a lot of the physics, basically almost all the physics, boils down onto the single pencil of interest containing the point P. The auxiliary piece is important for describing general states, but it kind of just goes along for the ride, and the content of the auxiliary stuff doesn't play a huge role. Okay, so let me take a second to talk about what is the state of the pencil. We said as A goes to 0, it looks more and more like the vacuum. The first order correction to that will be a single particle state. So we will, we consider basically a Euclidean path integral for that first order correction. Here I'm, preparing the state at some time t by turning on the source of an operator d phi that's localized to, its support function f for its smearing. Okay, so written out fully, this is now the global state. Okay, it's got two terms as an expansion of written as an expansion of A and as a function of lambda. There's two terms. The first term is basically the vacuum on the pencil tensored with whatever else is in the system, and then this first order piece is the one particle state on the pencil, kind of entangled with the rest of the system. Okay, but again, we're just kind of, for the purposes of this work, all you really need to pay attention to is that the state of the pencil looks like vacuum plus one particle excitations. Oh, and one interesting kind of corollary that came out of this analysis was that we showed in order to have a finite sandwich-Renyi divergence with respect to the vacuum, we found what we call the wedge condition on F. Okay, so Basically, in order to get finite SRD, F has to be localized close to the complement region, and how close it has to be is determined as a function of Renyi parameter n. And the intuition here is basically, if you are allowed to turn on sources close to the region R, then by observing close to that region, you can see that it's not the vacuum.
Sorry, what's SRD?
Oh, sandwich Renyi divergence. So it's the SN. Yeah, thanks. Okay, cool. So now that we have a general form of states in free field theories, we can basically evaluate the Renyi divergence, SN, or the SRD, with respect to the vacuum. This actually had a lot of, it's very calculation heavy paper, so I'm glossing over a lot of the details, but I'll be kind of highlighting some important points that really enabled this to happen. So first is that even though this is a general state with respect to the vacuum, the particular form here can actually be rewritten as the Renyi divergence between two nearby states. So here we had an arbitrary state with respect to the vacuum. Now we're taking the SRD of some state plus a perturbation relative to that original state. Okay, and this was useful because perturbative Renyi divergences were studied in 2018 by Ihano and May, so we can import their perturbative SRD results for this calculation. Okay, and then after that, basically taking two lambda derivatives and knowledge of the pencil state and some contour manipulations, we get the following expression. It's basically a sum over integrals of like modular frequency modes of the state. The details, again, aren't super important here, but what I will highlight is that this is manifestly positive because the functions f and q are both positive, and then we're taking the mod squared of m, which captures all of the state dependence. Okay, so basically kind of by brute force, this proves the Renyi QNEC for all n less than 1. And, oh yeah, importantly, though non-trivially, if you take the limit as n goes to 1, this reproduces the results in the original free field proof of the QNEC. Okay, good. So the other kind of big main result was that for n less than 1, we actually show that the Renyi QNEC does not hold. Okay, so calculation-wise, the procedure is pretty much the same, but we get one extra contribution from a pole in the contour integrals. Okay, so now we get a sum of two terms. The first term looks the same as in the n greater than 1 case, and then we have a pole contribution. Notably, this kernel f is no longer positive for n less than 1. So what we're seeing is basically that Sn double prime isn't necessarily sign definite. Okay, it's not manifestly positive like it was in the other case. And more importantly, we were able to find an explicit state that makes this contribution negative, meaning that we get a sum of two negative terms, and hence a violation of the Renyi QNEC for n less than 1. Okay. Oh, and one thing I should point out here is that our free field proof relied on this technique of null quantization, which only applies in d greater than 2 because you need 2 dimensions to split into pencils. So if you only have 2 dimensions, you only have a single pencil. But interestingly enough, for this counterexample, the state continues to be valid in 2 dimensions. So this actually shows that the Renyi QNEC doesn't hold for n less than 1 in all dimensions. Okay, so this is kind of the endpoint of things that are really airtight that we showed in the paper, basically proving the Renyi QNEC for free field theories in n greater than 1 and a counterexample in n less than 1. For the remainder of the talk, I'll be talking about some numerics and then partial progress towards generalizing the free field Renyi QNEC. Okay. So the first kind of regime of validity that breaks down is the two-dimensional case. Here we also, I guess, investigated 1+1 CFTs via critical spin chains. It was actually studied in 2017, or the relative entropy in CFTs had been studied by Nakagawa and Ugajin in 2017. There they were basically studying the Ising model, and knowing the operator content of that theory, they could analytically compute what is the relative entropy between the, I guess, the spin excitation relative to the vacuum. Okay, so that's, for example, plotted in this dashed line here. And the way to see that your spin chains are really probing conformal physics is that you can basically compute, you can diagonalize your Hamiltonian, compute the first excited state, and then plot the relative entropy with respect to the vacuum for different sizes. Okay, so here I've plotted it for, even as small as systems of 8 spins, you see that it kind of collapses to this curve. And on top of that, what we did was we calculated the sandwich-Renyi divergence, or SN, numerically for these states in the Ising model. Okay, and so the Renyi QNEC is the statement that the second null derivative is positive. For critical spin chains, when you find eigenstates of the Hamiltonian, you can exchange these null derivatives for spatial derivatives. So the second derivative being positive, you can really read off as a second spatial derivative here. And you can kind of visually see that there's no violation of the second derivative being positive here for various n, mostly centered around 1. Okay, and this is evidence that it continues to hold in 2 dimensions. It's far from a proof, but we were also able to check this for other critical spin chains that are also dual to free CFTs. Okay, and I guess also to our knowledge, this is the first calculation of sandwich-Renyi divergence in critical spin chains. Okay, so in this last slide, I'll talk a little bit about some partial progress towards generalizing to interacting theories. And again, the thing that breaks down here is the fact that null quantization doesn't have this nice pencil factorization structure. Okay, but what we were able to show is that if you consider not just general states, but near vacuum states, then you can use these same perturbative results of sandwich-Renyi divergence by Ihano and May. And interestingly, we find that the Renyi QNEC is saturated. So it's not, the second derivative isn't positive, it's strictly 0 at leading non-trivial order. So this would kind of play very nicely with the other papers. I forgot to put the citations here, but connecting energy and information via the QNEC. Okay, and I guess for technical reasons, I'll point out that this makes similar assumptions about a twist gap in the theory that Balakrishnan and collaborators make in their QNEC paper. Okay, and if you repeat this also for other divergences, not just the sandwich-Renyi divergence, we also found saturation to leading non-trivial order. Okay, so just to kind of wrap up, the things that we showed explicitly were basically a proof of the Renyi QNEC for free theories for all Renyi parameter n greater than 1 in dimensions greater than 2. We have an explicit counterexample to the Renyi QNEC for n less than 1. And we were also able to probe some numerics for the 2-dimensional case. Some future directions, mostly these are based around generalizing what I talked about on the last slide, finding subleading corrections for interacting theories or different divergences. Another very interesting question is off-diagonal derivatives of the Renyi entropy. So studying deformations of the entangling surface, not just at the same point, but at different points. And then another interesting thing to study would be deformations away from criticality in these spin chains. Okay, and the final message that I guess I'd like to leave you with is that, I think we should take this connection between quantum information and quantum field theory very seriously, and I'm hopeful that it has more to say about QFT and quantum gravity in general. So with that, thanks, and I will take any extra questions.
Thanks, Vincent. Any questions? Actually, I have a question. So, so in the free field case, if you take the slice to be slightly time lag rather than the light cone, rather than light sheet, well, what does, so I guess the different pencils will start to couple, right?
Yeah, I think you like it would still be true, but it's just not as obvious like how to do the analysis in that case.
Do you expect there is like the quick QNEC quantity will remain like, I mean, it will behave smoothly with that angle?
Sorry, I missed the beginning of that question. Could you say that again?
Do you expect the Renyi QNEC will be similar from the light cone, the light surface?
Oh, I mean, for free field theories, like if you take any slice, it's still the same state. So I would still expect it to hold. If you took your state to be not like just off the null plane.
Maybe you're asking about a space-like version of the QNEC. That.
Oh.
No, I'm just thinking like if you are integrating not along a light sheet, but sorry, if you are, so you say it doesn't really matter.
Yeah, good. I mean, the statement that you end up getting is about this, like, about the derivative at that point on the slice. So in that sense, it doesn't matter whether you actually consider the state on the null plane or just off.
Okay.
Rafael, I think you had your hand raised.
Yeah. Yeah, I mean, you listed a bunch of really interesting future directions. There's clearly a lot of very concrete things, calculational things that you can do, and that's what should be done. But on a more, I don't know, philosophical note, you talked in the beginning about how the QNEC originally was found by thinking about quantum gravity, even though it's a quantum field theory statement. What about this version of the QNEC? Can you go backwards now? And is there some property of gravity that might have required this, or at least led us to expect that somehow would tell us why it should work for n greater than 1 and not less?
Yeah, this is a really good question. I think our preliminary discussions were that this is very difficult to answer. I don't know, Pratik, if you want to say more. It's certainly like, it seems like it would be nice if there's something, but we haven't been able to come up with either, you know, what the backwards implication is or what this has to say in addition. But yeah, maybe Pratik, if you have thoughts.
Yeah, I guess it wasn't clear. Like, I mean, maybe in ADS-CFT you might try doing something like with adding branes to the bulk or something like that and seeing what this actually means. But in like general quantum gravity, it wasn't clear like what would a Renyi version of like focusing or something like that mean.
Well, it wouldn't be. It would still be really interesting if you could first figure it out in ADS-CFT.
Yeah, yeah.
I was wondering whether these sort of area eigenstates might play a role in this, since they do seem to come into.
Yeah, it should be helpful. I mean, we thought about this for a bit, because we wanted to try to prove this holographically first, but it wasn't like the bulk dual of these sandwich Renyi divergence didn't seem like something very easy. The area eigenstates might help, but yeah, I'm not sure.
And my second question was, well, you also pointed out that for condensed matter systems or general quantum mechanical systems, it's not that hard to find violations of the QNEC and presumably of this version of it. And so I think it would be interesting if one could somehow characterize the theories in which the QNEC holds in some way, like are those relativistic field theories? What does it take? And I was curious whether, again, this would give you more of a handle on that problem.
Yeah, it's certainly very interesting. I think one thing that was like nice about this particular method was that like it was like it kind of collapsed to the analytic value of the relative entropy, even for system sizes that are really small. I think in general, like basically the analogous statement you would like to say is something like, if the spin chain can be modeled as a low energy like QFT, then you would expect this to hold. But those, at least I'm not an expert in calculating these finite end corrections. And for other quantities, it wasn't so obvious that we were in a continuum limit. But that is certainly, yeah, a very interesting question to ask.
Yeah, maybe it's more the kind of question that you want to come back to after you've done all the other things on your list, which seem really interesting. I mean, I think there's a lot to do there. Yeah. Thanks.
Just a bit related with Raphael's first question, Pratik and Vincent. Is it possible, or did you think that this Renyi version may be related with the bulk geometry, which is branched into n seeds, and the general relativistic kind of property of that kind of geometry, possibly with the cosmic brains or something?
Yeah,
because
actually,
essentially what you need to get is a low to the n instead of row.
Right. Yeah, I don't think we thought too much about the bulk dual of this particular divergence. We did spend some time looking at the refined Renyi divergence dual to Xidong's holographic brain prescription, but it didn't come out as nicely. So we focused on this.
Yeah, that's great. Thanks.
Yeah. Patrick, did you have a question as well?
Yeah, I saw Patrick has a hand raised previously.
It was raised, but Raphael basically asked my question better than I would have, so it was taken care of.
I see. Okay.
Good. So with that, let's thank Vincent again.